which is actually very similar to just local reactions in the RDME. And the theory for local reactions also connects to the theory for nearest neighbor reactions. So first, I'll spend some time on that, and then I'll move on to nearest neighbor reactions. So first of all, yes, the RDME, so I'm guessing most people in here are familiar with it, but just to make sure, I'll just say some words about it. So this is supposed to illustrate like how we can simulate exact reactors of the RDME. So what we got is some volume, in this case a square, which is discretized by Cartesian mesh into voxels of equal width. And in each voxel we've got molecules. Keep track of the exact position of the molecules inside the voxel, just count the number of molecules. And diffusion is simulated as discrete jumps between these voxels, and reactions occur when molecules are occupying the same voxel with some intensity given by the reaction rate. So first, just some notation. So throughout this talk, I will consider only structured Cartesian meshes, specifically with periodic boundary conditions, but that's not a super important assumption. You can get away with reflective boundary conditions too. But it's a little nicer with periodic boundary conditions. So L will denote the width of our box or square or line. V will be the volume. H is the width of a voxel. So we'll call that the voxel size. N is the number of voxels, and D will be the dimension. So we're talking about the RDME and reaction rates and accuracy of the RDME. We have to compare it to something. So what I'm comparing to is this microscopic model, so specifically this Stochastic model. So we're approximating molecules by hard spheres. They move by normal diffusion and then they react with some probability when they collide. So this is my attempt at illustrating this. So we've got two molecules diffusing around, and when they collide, you can form some products. And this dynamics is governed by the Stochastic equation for a pair of molecules. So the PDFP for the relative position of two molecules solves the diffusion equation with a boundary condition at sigma, where sigma is the reaction radius of the two molecules. So Kr is the intrinsic or microscopic reaction rate. D is the diffusion constant. So this is for a pair of molecules, and then for a full system, there are different algorithms for simulating trajectories, for instance, the GFRD algorithm, which is fairly popular and efficient. So this is for associations, and then associations are basically you sample, we've got some dissociation rate KD, we sample an exponential, dissociation time exponentially distributed, and then when molecules dissociate, they are placed in contact. So at the reaction radius sigma. And this can actually be incorporated into this boundary condition if you want to. So this will be our sort of fine-grained model that we compare the RDME to. So what we want is basically we want mesoscopic. We want the mesoscopic parameters, specifically the reaction rates. And to get those, it's useful to first look at how we can get the effective rates, or the well-mixed rates, if you wish. So if we're considering, you can consider a single reversible reaction with some intrinsic or microscopic rates Kr and Kd. Question then is, given these microscopic rates, how do we get the effective rates denoted by Kr effective and Kd effective? I mean, this is pretty standard. This is well known, of course. So if we let tau diff, that's the average time. So the setup is as follows. We've got one molecule fixed at the origin, for instance, and then we consider the relative motion. So let's say that A is fixed at the origin, B is uniformly distributed, and then tau diff is the average time until these two molecules are in contact for the first time. That's sort of the diffusion part of the reaction. The second part I call tau rebind. So that's the average time until they react, given that they started contact. I mean, that's exactly the rewind time. Like after the association, they're placed at contact. And the effective binding time, tau f. So tau effective is just the sum of these two parts. So it's the diffusion part plus this part. And these two, they're both known. I mean, this is the diffusion part derived by Collins and Kimball in the 40s. It's just the volume over this. This part is just the volume over the microscopic rate, and the effective binding time is just the volume over the effective rate. I mean, that's by definition. So we just plug everything in, and we can solve for the effective rate.
Can I ask something very, very silly?
Sure.
I thought that in 3 dimensions, sort of like Brownian motion is not supposed to come back in some sense. So how should I think of that with relation to the tau diff there?
So the molecules, they're actually spheres. So it's true that it never comes back to a point in 3D.
Okay.
But since I mean, you got a finite volume.
Whoa. I mean, I think he still has a point, which is, if I'm not mistaken, because Brownian motion 3 dimensions is transient, you can wander away at some finite probability and never come back to a given compact region. I think that's what he was asking.
Not in a finite volume.
Yes. So basically what you said.
Okay.
Yeah.
So here, if I take sigma to go to 0, which would be the point particle Brownian motion, that would go to infinity.
Yeah. But I mean, also since we're considering a finite volume. That's important, of course.
Okay.
Yeah.
Okay. Thank you. Sorry.
Yeah. No, that's fine. Yeah. So we get this expression. And then the question is then, so that's how we get the effective rate. So how do we get the mesoscopic parameters? I mean, the diffusion coefficients, they're fairly straightforward, right? We discretize the diffusion equation. We can do that with a finite difference, finite differences, or if we have an unstructured mesh, we can do it with, for instance, finite elements. But the reaction rates are slightly less trivial. One simple case is if you have a well-mixed system, basically. So either the diffusion is very fast or the reaction is very slow, or I mean, it's actually the reaction is slow compared to the diffusion. So let this Kr meso, let that be the mesoscopic reaction rates, right, in units per second. Then for a well-mixed system, it will just be the effective rate scaled by the volume of the voxel. Simply because if the system is well-mixed, the molecule is uniformly distributed. And the reason that I'm showing this is that this is what a lot of people actually do. And this is what people do in a lot of the software that's available, actually. The problem is that this holds only for well-mixed systems. And typically, with the RDME, I mean, we're interested in something that's not well-mixed. So, I mean, this is what can happen. So, this is just an irreversible reaction that is very diffusion limited. And if you look at the average time until the molecules react, this is what you get. So the x-axis, we have the voxel size, h, as multiples of the reaction radius. On the y-axis, just seconds. The red dashed line, that's what you get on the microscopic scales. I mean, it's obviously independent of the mesh. It doesn't depend on any mesh. So this is sort of the exact binding time that we compare to. And what we see on the mesoscopic scale, if we just plug this in, the well-mixed rates, we get something that actually gets worse and worse. I mean, this works pretty well for large voxels, because that's what it's sort of derived for. But as we refine the mesh, it actually gets worse and worse, and diverges as h tends to some small voxel size here. Another example, so if you look at the sequence of reactions, so I mean, this is obviously a bit unrealistic, but you can imagine a system that has a behavior that is similar to this, like something could happen fast with one of these molecules, and you could have this sequence of reactions. And if you compare the mesoscopic simulations with the mixed rates to the microscopic, this is what you get. This is the L1 error, the relative L1 error. And this N here, that's the number of voxels. So as you refine the mesh, basically nothing happens. There's no convergence. So the question then is, what if the system is not well mixed? So how do we get the reaction rates? And it's pretty much the same approach as when you get the effective rates. So in this case, we just define, instead of tau diff being the time until they're at contact, it's the time until the molecules occupy the same voxel for the first time. So that's sort of the corresponding mesoscopic tau diff. Tau rewind, that's then the average time until they react, given that they start in the same voxel. That's also the rewind time, exactly the rewind time. So you can write the effective mean effective binding time as the sum of these two. And as it turns out, you can derive both of them. So the rewind time on the mesoscopic scale is just the number of voxels over the mesoscopic reaction rate. And it's pretty straightforward to get this. It follows from a theorem by Montreux from the 60s on random walks. So basically, the number of steps required to return to the RG voxel is exactly the number of voxels. This holds in 1D, 2D, and 3D, actually. So all this holds in all three dimensions. And what you get then is this, so you just solve for the reaction rate, and you get, well, the number of voxels over this. Some people might prefer to write the number of voxels as the volume over the volume the voxels, so you'll get 1 over the volume of the voxels and then something here. So what remains then is this diffusion part, and as it turns out, we can get that too, at least some expansions of that. So this is also also follows from the theorem by Montreux, saying that if a molecule starts uniformly on a mesh, then the average number of steps, which is the origin, will be given by this in 3D, this in 2D, and this in 1D. I mean, it's worth noting, it's well known that these two actually diverge as the number of voxels increases. So this diffusion, this time here, the diffusion, it just keeps growing in 3D and 2D, which indicates that you can't refine the mesh beyond a certain point. But in 1D, it actually converges, and you just get the length squared over 3 times the diffusion rate. So I mean, to get the reaction rates, we just plug this into this. I mean, the effective binding time is just the volume of this. And you can relate this to the microscopic parameters by using sort of the Collins and Kimball expression from this. So worth noting here is that this expression, the sort of the well-mixed rates, that obviously holds only if this part is much greater than this. So that the fusion part is like a small part of the process. And I mean, we can just plug that in, and we get that for this to hold, the voxel size should be much greater than this in 3D and much greater than this in 2D. So that's a simple test to see if this actually is a good approximation or not. Another thing to note is that this holds if h is much greater than this, but for this rate to be well defined, I mean, this should be positive. This has to be greater than that, so that means that h should be greater than or equal to these two for rates to be well defined. I mean, that's intuitive. I mean, if the diffusion part is much slower than the actual reaction, that doesn't make any sense. So what we get then, so we can actually derive sort of the smallest voxel size for which we can match the effective binding times. And so we call that smallest voxel size H star KR. And if we just H equal to this and plug in the expressions for K, F here, we'll get the smallest voxel size in 3D will be 3.2 times the reaction radius, and in 2D approximately 5.1 times the reaction radius. I mean, this is somehow like a worst case scenario, like when KR tends to infinity. So if we find a KR, this will certainly be smaller. But what we can notice that for H equal to this, independently of KR, the diffusion, the mesoscopic tau diff will equal the microscopic tau diff, which means that the rebinding times will also be equal for H equals H star. So what we have is actually that for H greater than this, the mesoscopic rewind time will be greater than the microscopic rewind time, which is intuitive as, I mean, if a molecule dissociates in a voxel, then there isn't uniformly distributed, so the rewind time should be greater. For H at this lower bound, they're equal, but then as H keeps decreasing, this will actually be smaller than that. So we can't really expect to get more accurate results. That's where we find the mesh below this lower bound, independently of KR. So somehow, I mean, that's in the general case. I mean, I'm sure you could come up with examples where it does, but in general, you won't approximate the microscopic dynamics better for H below this lower bound. This is, if we look at the, so this is the mean rebinding time. So if we look at the, it's interesting to look at the distribution too, to make sure that we're actually approximating the distribution as well. So the blue line here, that's the rebinding time distribution. And the red line here, that's the mesoscopic rebinding time distribution for a mesh size above H star infinity. The yellow dashed line, that's when we're at H star, and this is when we're below H star. So we can see that we get the best match actually for H equals H star. And we also note that I mean, over here it doesn't match, and that's when we're at a time scale that's shorter than the voxels, sort of the corresponding time scale of the voxels, so to say. So if we look at this example again, this is what we got when we just used the well-mixed rates, and this is what we get when we use these rates where we didn't assume that the system is well-mixed. So it seems to converge pretty nicely, at least down to here.
So just to understand so does that mean that if you were to find the value of n that corresponded to this H star, this would actually be 0?
I mean, there's some statistical error here, so I don't remember exactly where H star is here, but yeah, so this is just the mean, so the mean error, so it would be very close to 0.
But you have estimated that during when you say statistical error, this is by Monte Carlo simulations.
Yeah, yeah, that's right. So I think this is close to the statistical error. I mean, so yeah, I should point out that here I'm computing the error in the mean, so I mean, I'm not claiming that the RDE actually converges to this Molchovsky model, because I mean, we have point particles in the RDE, so there's no excluded volume or anything like that. So I mean, when I say convergence, I mean in a specific sense, not in, it certainly doesn't converge to the actual equation in that sense. Okay, so that's for local reactions. But the question then is, so the idea is, what if we want to resolve space to even more than we can with local reactions? So the question then if we allow molecules to react when they are in neighboring molecules, what happens to this H star? Can we push it down further? So that's what motivates this work. First, there's a bunch of notation. So unfortunately, there's quite a lot. So I hope that you'll be able to keep track of it, follow it anyway. But in this case, we'll have two parameters. It's not just the reaction rate. So we'll have R. So we'll say that the molecules A and B, when they will react at intensity 1 minus 2 times the dimension times R times this Kr meso when they are in the same voxel. And then they react with this intensity when they are in neighboring voxel. The reason is that we want the sum. So if we sum up over all the voxels, we want the intensity to be constant. I mean, that's easily seen if you consider a uniform distribution of one of the molecules and the other molecules diffusing in this uniform distribution, then the intensity should be constant. So by introducing this R in Kr meso, we can keep the intensity constant. R should be greater than or equal to 0, obviously, and less than or equal to 1 over 2d, such that this is greater than or equal to 0.
Maybe I missed it, but you were saying that the reaction radius is bigger than a voxel size in the second case?
No, so R is just
How they
parameter.
react?
So this is on the mesoscopic scale. So we basically just have point particles jumping between the voxels. So I mean, maybe I'll just do it. Since we got it here like this. Then you got 1 minus 2 dr. They are meso here, and then in all the neighboring voxels we got this intensity. So that's one thing. And then if you sum it up, it'll be Kr. And then we're interested in the time tau R1, the average time until the molecules react given that they occupy neighboring voxels. So analogously, tau R0 is the average time until they react given that they occupy the same voxel. And then tau rebinding, that is the same thing as the rebinding time, the time that until they react given that they just dissociated. And tau diff in this case will be the average time until the molecules occupy neighboring voxels for the first time, because that's the first time when they could, in theory, react. The first thing we have to do is consider dissociations, because depending on how we do dissociations will sort of affect how we derive the reaction rates in this case. So the question is, following a dissociation, where do we place the products? And this is not completely straightforward, actually. So let's say that we have a system like this. And S1 dissociates, so it's a unimolecular reaction, so it makes sense to place these in the same voxel. They're dissociated. And they can react to form S2, and then S2 dissociates, and then where do we place these two when S2 is associated? I mean, for a reversible reaction, it will make sense to place them according to these probabilities, right? That would be the first thing, I think, and that would probably give you the most accurate result for just a single reversible reaction. The problem is when you have several reactions like this. So you have different rules for these dissociations. So if you place these in the same voxel when this dissociates, then this dynamics will be wrong in a short time scale. If you do something different here, then some other dynamics could be wrong. So different rules does not work in general. On the other hand, I mean, you can argue the same way that, okay, well, let's say that we do the same thing. So we've got these probabilities. Why not just place them according to the same probabilities when this happens? But I mean, we could easily construct a system where that wouldn't work either. So the same rule does not work in general. So somewhat arbitrarily we decide just to place them in the same voxel with probability 1. So I mean, so that it's well defined for all dissociations in the system. So this actually contradicts that. So what I mean here is that you can't take these probabilities and then say that then apply it to all dissociations. I mean, that's not going to work. So with this notation, so this is very similar to what we did in the local case, but it's just slightly more complicated. So again, we can write the effective binding time as the diffusive part plus this tau R1, which is the time until they react, given that they are one voxel apart. Now the rebinding time is replacing molecules in the same voxel. It's not exactly this, but it's the time until they react, given that they start in the same voxel. So what we need is to relate these two, and we can do that as follows. So this time, so given the two molecules are in the same voxel, they jump, say with probability p jump. So this time will be p jump times the time for an event in this voxel, plus the time until they react, given that they are one voxel apart. Because following a jump, it will always be one voxel apart. Plus the probability they don't jump but react times the average time for that event. That's just this. So we can easily relate this time to this time through this, and the reaction rates will show up in these expressions. So this time and this probability will depend on the mesoscopic rates and the parameter R. So I'm realizing now I'm using R here. That stands for reaction, not, it doesn't have anything to do with the parameter R. So in the local case, we basically said, yeah, we want to match the effective binding time. But in this case, we have two parameters, so we really should have two constraints. I mean, the first constraint will still be that we want to match the effective binding times. So this should equal this. Second thing we do is that we say that we want to minimize the difference in rebinding time. So we know that in the local case, the mesoscopic rebinding time approaches the microscopic rebinding time, tends to H star. So we certainly wouldn't want this to be worse in this non-local case. So we're saying that this should be as small as possible. We want to approximate this as well as good as possible. The first thing we'll do is that we'll derive this tau R1. And it turns out that we can get will be this. And this is fairly straightforward. So what we're doing is we're basically using a bunch of theorems by her, the theorem by Montrol again. But we'll have to derive a couple of extra things. So if we let Mij be the average number of steps to reach voxelate distance j from the origin, given that we started with this of I, and we'll let Msj be the time until we reach voxel distance j, given that we start uniformly on the mesh. We can derive these expressions. So this is saying that this is from the theorem by Montrol. So this is saying that the time to get back to the origin voxel is just n, the number of voxels. And we can get this from this, which is also from Montrol, and then we can get these recursively, and they're fairly straightforward. And with these, we can just list all possible cases, like what can happen. So given that it starts at a voxel distance 1, it will either jump to the origin voxel or jump one step up. And then using these, we can sort of get it recursively. The second thing we want to derive is corresponding H star infinity. So the smallest voxel size such that we can match the effective binding time for Kr in this case, I'll just add a G here, that's for the generalized model. So in this case, we get that the smallest voxel size will be approximately 1.6 times sigma in 2D and 1.8 times sigma in 3D. I mean, this is easy to derive. You know that this diffusive part is just this term, which we derive here, times the average time for a jump. And then we just solve these. When the mesoscopic, and the diffusive part in the mesoscopic scale is the same as the diffusive part in the microscopic scale. Then we get this. So I mean, this is promising in a sense. This is much smaller, or it's smaller than what we had before. So we're almost down here to the size of the molecules, some of the reaction radii. But we still have to determine these parameters. So it turns out that it will be useful to consider 3 different cases. So the case 1 will be that h is greater than or equal to h star infinity. So that's the minimum mesh size, smallest mesh size in the local case. The second case is that it's smaller than that, but greater than the minimum mesh size in the generalized case. And then the third case is that h is, it should be h star infinity g. So that's when it's smaller than this. And what we can do in the first case is to show that, assume that these 2 parameters satisfy the first constraint, that it's matching the effective binding time. And we can show that for all h greater than or equal to h star infinity, the mesoscopic rebinding time for positive r will be greater than or equal to the mesoscopic rebinding time for r equal to 0. So r equal to 0, that corresponds to fully local case. That's when r is 0 here, so we have only reactions in the same axis. So this, for any positive r, this will be greater than this, and this is always greater than the microscopic rebinding time, which means that this will always approximate the microscopic rebinding time worse than we do in the fully local case, which means that for all h greater than or equal to h star, the generalized RDME reduces to the standard local RDME. So that the local RDME will be a better approximation than this for all h greater than or equal to that. This is how we can show that. So basically, we're writing the effective binding time in terms of the local terms here and the non-local terms. No, I mean, these are obviously the same. And we're noting that, I mean, we're just writing out the diffusive part in the non-local case, and in the local case, the difference here, it has to be 0. Plug these in, and we get that the local rebinding time is tau r1 minus something. So this is a way of just connecting the local rebinding time with the term in the non-local model. So to show this, showing this basically reduces to this. We can just plug everything in and solve. Verify that this equation holds. The second case is that h is between these 2. And then it turns out that in this regime we can both match the effective binding time and exactly match the rebinding time. And we do that for QR meso equal to this and R equal to this. Or Q is this. So unfortunately the expressions are not as nice as in the local case. But I mean it's fairly straightforward to derive these. I mean we've got all the we're basically just plugging everything in and then doing a bunch of algebra and we get this. So I mean, the proof is really just, we're assuming that we can match both of these, and then we solve for both parameters. And once we've done that, we just have to verify that the parameters are actually well defined, that the reaction rates are positive and the R satisfies that inequality. And it turns out that it does. So we actually got an analytical expression for this. The third case, it's analogous to the local case. In this case, this mesoscopic local rebinding time will be smaller than the microscopic rebinding time. So in general, we can't expect to gain any accuracy by going below this. This will actually approximate this worse than we do for H greater than this. So I haven't mentioned the dissociation rates, but I mean they follow from the association rates by just saying, well, the steady state should be the same on both scales. And by matching those two, we just get that for the local case. I mean, it's just this has to satisfy detail balance. And in the local cases, we're matching the rebinding time and effective binding time, then the dissociation rates will be the same too. So to summarize, for H greater than this H star infinity, we have local reactions only. H between these two, we have non-local reactions according to the formulas on previous slides. And for H smaller than this, generally we don't gain anything by going down here, so there's really no point. So this is what happens then if we look at the distributions. So for the rebinding times. So I mean the hope is that we gain a little bit. So there are a lot of stuff in here. So first of all, the red dashed line and the yellow dotted line here, they're from the standard local RDME. So the red dashed line, we see that approximated pretty well up to here. That's the time scale of H star infinity. This is when H is smaller than H star, so it's just 0.95 times this. You can see that it's already pretty far off. Then we've got the purple line here. That's when we're a little bit bigger than this H star infinity, generalized case. And we can see that it matches pretty well up to this line, which is the time scale of this H star infinity G. But I think what's interesting here is to see that when we pick the voxel size to be this H star infinity G, we get this green dashed dotted line. We can see that there's some strange behavior here, and that's because we made this assumption that associating particles are placed in the same voxel. And as H decreases, we'll have more and more reactions in the neighboring voxels, and less in the same voxel. So by placing them in the same voxel, we're introducing an error that will be significant once H gets really small. So in this case, I mean, it actually looks like we're matching the distribution best somewhere in between maybe this H star infinity and H star infinity generalized case. But there's really, I mean, no matter how we place the products, we'll never be accurate beyond this point, because that's I mean, we're not resolving space more than this. Okay, so last numerical example. So this is not the system that I'm actually simulating, but I want to show this to show how it relates to a more realistic biological system. So this is just a model of a map K cascade. This was studied in this paper by Takahashi and collaborators in 2010. So in this paper, they're showing basically that the microscopic method different results from mixed models, and also the RDME mixed rates. So what happens in this model is that first you got this. I mean, the map K is phosphorylated in 2 steps. So you got this reversible reaction, and then this dissociates into these 2 molecules. And then this molecule is quickly, or it's reactivated with some intensity K7. This molecule, and then these 2 can react and form this pair, and then this dissociates, and you've got sort of this sequence, and then this molecule dissociates, and then this can be reactivated, and these 2 can So, from a numerical perspective, I mean, trying to look at the sort of a worst case scenario where the numerical methods will have problems. Then it's interesting to take this K7 to infinity, say that this is infinitely fast. So this dissociates and then these can rebind instantly. Right away. So you'll get a lot of very fast rebindings. And if you do that, I mean, basically the behavior is reduced to this system. So you say this dissociate and then they can rebind and form S2, and S2 dissociates and these can rebind and form S2. These are the parameters. So the point here is that these molecules have different reaction radii, meaning that the smallest is H star infinity. For this reaction, it's different than the H star infinity for this reaction. So we need different mesh sizes for each reaction to resolve it. Actually, that's what we'll see. What we can see here. So the first reaction has a lower bound on the mesh size of 5.1 times 10 to the power minus 9. The second reaction has a lower bound that is about twice that in the local case. But in the non-local case, we have a lower bound for this reaction of 3.9 times 10 to the power minus 9. So the hope is that in the non-local case, we'll be able to go down to this mesh size. And since this mesh size is smaller than both of these, we can resolve it in the non-local case. But we might have problems then in the local case, and that's what we can see here. So on the left, I plotted the average number of S3 molecules over time. So the red thick line here, that's the microscopic results. This red line here, that's the standard RDME for some mesh size greater than the smallest possible mesh size. And this is the standard RDME as we take H smaller than the smallest, in this H star infinity. I mean, we can see that here we get something that underestimates the mean, and here we get something that overestimates. I mean, sure, somewhere in between we get something maybe that is a good estimate of the average of this S3 molecule, but the problem then is that we won't get the right amount of the other molecules necessarily. And also, we don't know exactly where that would happen. So, on the other hand, if we do this with a generalized RME, we got this purple line for some mesh size, and then as we refine it down to some fine mesh size, that resolves both of these equations. We see that we get a very good match with microscopic results. That's what we can see this behavior here. So this is the L1 error. So this is not the relative error, but the absolute error. And this is the mesh size. So the purple line here, that's the spatial resolution that we need for the second reaction, and this is the spatial resolution that we need for the first reaction. This red line here, that's the error if we only have local reactions. And as we can see, the problem here is that as we start getting down here, we're resolving this reaction. Or it's not a problem with this reaction, but we're below this minimum mesh size for the second reaction, meaning that the error increases. We're actually simulating the second reaction worse and worse. So it never really converges. I mean, we may, as we go down here, we're approximating the first reaction better and better. But we're doing this worse and worse. So it goes down for a little bit and then it starts going up again. So we never really converge. But if we allow nearest neighbor reactions, it can actually go all the way down here. So this is the minimum mesh, the smallest possible mesh size for the second reaction. So we can go all the way down here and resolve both of these reactions. So we get a very small error. Some things to consider. So first of all, So it works, but I mean, I have to say something about efficiency. So obviously, in this case, we're at a spatial scale that is on the order of the size of the molecules, which means that we'll simulate a lot of diffusion maps. So this method is, I mean, it's not going to be efficient if you just have like a uniform fine mesh. And in fact, methods that directly approximate the Stochastic model might be more efficient in this case, e.g. the GFRD. So that's the algorithm that I use to get the microscopic results. And for the finest mesh sizes, this is certainly a lot faster. In general, it might not be. It depends on the number of molecules and so on. But in some cases, it can actually be faster. The second thing is, I mean, I've constructed this example is constructed to demonstrate this thing, but you could easily construct an example where even this, like the generalized RME, wouldn't work. I mean, you could consider 3 reactions with different reaction radii, requiring different resolution, it still wouldn't work. I mean, it would work better than the local RME, but it doesn't always, it's not always going to converge even in mean. So the question then is, when is this useful? So if I'm saying that it's not very efficient, so one thing that I'm thinking about is hybrid methods. For instance, you can couple the RDME on different mesh sizes. So if you won't simulate the whole system on the finest mesh size, only the part of the system that requires it. It can also be the parts of space require very high spatial resolution. So maybe you can get away with doing it parts of space, not everywhere. So I'll just briefly mention the case of unstructured meshes. So this was all on Cartesian meshes. In some cases, we want unstructured meshes maybe because the geometry is complicated, so it might be simpler to resolve it with an unstructured mesh. So this is stuff I'm working on. It's not published yet, but in principle we can take a similar approach as for local reactions. You won't get the same nice analytical expressions, but we can use some numerical pre-processing. So we can compute some of these things numerically instead and can remain pretty efficient and accurate. So I also want to mention some related work. So Sam has taken a different approach to these non-local reactions in this paper. So basically, I think he talked about it before, but you can discretize a microscopic model. You can get reaction rates that way. Roddick and John Chapman published some work. So in this paper, they derive mesoscopic reaction rates in 3D on Cartesian meshes. Dylan Elf and his collaborators published this paper. So they basically derive mesoscopic reaction rates as spherical meshes. Should acknowledge my collaborators. So Linda Petzel, GCSP, and Stefan Hellander that worked with us on the local reaction rates.
Stefan, have you looked at any other statistics when you're kind of doing your error studies beyond the distribution of times, like a spatial statistic or something?
No.
Okay. I'd be curious, interested to see what that
sure,
looks like,
sure.
even for just like a simple example.
Mm-hmm. Yeah. I mean, if you're just looking at the rebinding time, I would expect it to be pretty good because I mean you're resolving. It's basically, I mean, at that scale, the diffusion part is very well resolved. But I mean, you could easily come up with examples where the spatial distribution would be wrong, like if you would consider excluded volume or something like that. Yeah, definitely wrong. So yeah, so it's not. I mean, yeah, it doesn't always work.
Yeah.
I think had two questions. I think you kind of answered the first one already when you said that, when you kind of resolve that fine, maybe you could sort of be using other methods. So what is so special about when you could sort of, I mean, in principle, I mean, couldn't you just go to sort of like secondary interactions? Why did you stop at sort of like first, like just neighbor, just the immediate neighbors, and not sort of like second neighbors or
Well,
something like that?
I think the complexity increases, it gets harder and harder to derive the expressions.
But would you expect, I mean, would you expect that you, because it's sort of like you almost got it down to 1, yeah, you got it down from 3 to 1. Would you expect that if you were to sort of,
I guess you would go down, but you wouldn't go down as much, I guess.
you don't think it would be less than 1 there?
Yeah, probably. The problem is that I don't know what I would do with the dissociation, where to place the molecules in the ion. So I worry that you'd still introduce that error that would still be probably on the scale of on the molecule side. So I don't know if you could gain that much in this case.
In that model, where, I mean, did you try to see what happens if you put them not just on the same voxel, for example?
Yeah, I did. So that was what I did first. So I didn't actually think about this at first when I started working on this. So if you just look at a reversible reaction, yeah, like I said, it makes a lot more sense to place them according to these probabilities. And if you just look at a reversible reaction, you'll actually match the rebinding time distribution much better. The problem was then that for some problems it doesn't really work, because you might have, like if you have multiple dissociations and they somehow interact, and these probabilities are different for each association, it doesn't, you still get that error.
But do you get the same error, bigger error?
You can get a bigger error, so you get an actual error in mean. Like when I'm looking at the mean statistics of the trajectories, I'll get an error, which I don't if I do it this way. That's because if I assume this, I mean, at least it's consistent, so I can exactly match the mean statistics. So I'll get the mean right. I mean, then I'll get the spatial distribution slightly wrong, for sure.
Okay, thanks.